Hello, and welcome back to Every Problem. This is Stewart Calculus 8th edition, section 1.1, problem 40. In this problem set, they're asking us find the domain and sketch the graph of the function. So this function here, g of t equals t squared minus 1 all over t plus 1. Kind of an interesting function because there's a lot of variables and it's a fraction and everything, but it, for the most part, behaves just like a normal line. That's something kind of interesting about this, and we'll go over that. So let's write this function out again. We have g of t equals t squared minus 1 all over t plus 1. And so hopefully there should be some alarms going off in your mind at least about this this t squared minus 1 at the top. That's what we call a difference of squares, and we can factor that out as a t plus 1 times a t minus 1. And this is over a t plus 1. And we'll go more over that soon. But for now, let's just find the domain. And so the domain, it looks like we could plug pretty much any number in here, except, I'll use red for this, right? Except for, in the denominator here, we cannot have -1 in the denominator. That is our only number here that is completely against the rules. So if we have a -1, that puts a 0 in the denominator. And now a big temptation, of course, is going to say, oh, well, we've got a t plus 1 here and a t plus 1 here. Why can't we just cancel out t plus 1s and have a function that's t minus 1? It's a very good question, but it all goes back to the fundamental idea of a function, which is that a function is a rule, and we can't change the rule however we want, right? We can look at the rule and we can use math to try to understand the rule better, but we can't change the rule. So that's part of the fundamental idea with a function. And because of that, t cannot equal -1, and we cannot just cross out t plus 1s on top and bottom. Because, again, this is a function, and it's not like a problem in algebra where it says, oh, just simplify, right? It's different. It's a different type of problem here. So we know that the domain is going to be equal to pretty much all the numbers except for -1. So for that, we'll go ahead and write the word domain, right? Domain being all inputs that give us some output. And we'll have open bracket, -infinity. The reason for the open bracket, of course, because we can't cut off infinity at any point and just say, oh, this is the end of infinity, right? So from -infinity to -1, but not including, that's why we have the open bracket. Then we're going to use this u here, this big U, which means union. That means, pretty much it means including. So we'll say including open bracket, -1, all the way up to positive infinity. So what we're doing here in our statement is we're including every number except for -1 itself. And that's the first half of our problem. So that shows us our domain. Now they want us to sketch it. So let's go ahead and do that. And we'll draw our coordinate grid here. And I'll write the function again by our coordinate plane. So it's t squared minus 1 all over t plus 1. We have t squared minus 1 all over t plus 1. Now, remember I said we would go back to this idea of t plus 1 times t minus 1 all over t plus 1. So let's come back to that now. When we factor it out, algebraically, it does look like that you could cancel out these terms here. What that means is that's called a removable point of discontinuity. So it's kind of a mouthful to say, right? Removable point of discontinuity. But what that means is that there is a hole in the graph. That's really all that means. And so let's just go ahead and start plugging in values. That way we can make some sense of this visually. So let's take a look at this top function here, or this function in black. So if we plugged in 0, let's say, if we plugged in 0 for our x value, we would get -1 over 1, so that would just give us -1. If we plugged in 1, that would give us 0, right? We'd have 1 minus 1 is 0 over 2, so that would give us 0. If we plugged in 2, we would get 4 minus 1, which is 3, all over, all over 2 plus 1, which is also 3. So that would just give us 1. So it looks like an input of 2 would give us 1. And what we can see is this actually has a very linear pattern to it. And I'll draw this in yellow, that way it's easier to see. So 0 gets us -1, 1 gets us 0, 2 gets us 1, and so on and so forth, except, well, what happens if we plug in -1, right? Well, t squared, -1 squared, that's just 1. So 1 minus 1 is 0, not a problem, right? Up here, 1 minus 1 is just 0. But here, t plus 1, -1 plus 1 is 0. That gives us 0 over 0. And that is undefined. So 0 over 0 is not just 0, it's going to be undefined. So that's where we have some problem. And that's where we're going to have, I'll draw this with a really slim pencil. So if we have -1, there's going to be this open circle, an open hole right around that point there. And the rest of the graph will behave like a line, just like this. And it'll just keep going, right? And so when we zoom out, it looks like everything's perfectly fine, except there's that one hole in the graph, and that's exactly at the point -1. And that's the sketch of our graph. So that's going to be it for problem number 40.